Okay, so as we were discussing in the previous lecture about unitary and orthogonal operators, we will end this part by discussing briefly about rigid motions. Okay, so what are rigid motions? So typically these are functions over real vector spaces which preserve distance. Okay, and the examples which we had talked about were such mappings which cause no change in the distance between 2 points. Okay, for example, a rotational operator, so it just rotates a vector by some angle, but if I choose 2 points on that vector, the distance between them is unchanged. Or if I reflect a vector about some line, still we have the same case, that if I have 2 points on that very vector, the distance between them is unchanged. So let me start afresh. These things I have briefly discussed in the previous lecture, but since we are talking about rigid motion, let's start afresh. So definition, so we start with a real vector space. Let V be a real vector space, or rather I should use the term a real inner product space. A real inner product space. Then a function f from V to V is called a rigid motion. Is called a rigid motion if the distance between fx and fy is still the same as the distance between x and y. Okay, and this is for all vectors in V. Okay, for example, suppose let's say I am in R2. Suppose I am in R2, and let's say I have a vector like this. Let's say I have a vector like this, and what I do is that I map it to, suppose here. So suppose this is vector V, and this is say the mapping of V under F. Okay, and I have just rotated it. What I am trying to say is that I have just rotated it. So let me just, yeah, so I have just rotated it. I have caused no change to its length or whatever. Okay. So my question is that if I choose 2 points on the vector V, suppose I choose this point x and this point y, then I'll get corresponding points here as, let's say, x and y. Let me draw it a bit bit bigger. Okay, yeah, this will do. So this is your y axis, this is your x axis. What I'm saying is that I start with a vector V and I just rotate it a bit here. I just rotate. Okay, so this is your say f of V. What I do is that I choose 2 points on V. Let's say I choose points x and y, and then by this rotation I'll eventually land 2 points corresponding to x to be fx and corresponding to y to be fy. But the thing is that there is no change in the distance between x and y when it gets mapped to fx and fy, right? And you can also observe that this is the same case if you do a reflection. You will have the same case if you do a reflection. Moreover, there is a standard notion that any orthogonal operator is a rigid motion, but we will come to that later. There is one more sort of an operator of which is a rigid motion, which is called a translation. Okay, so a translation is a mapping from a real vector space to itself. So V is a real vector space, real inner product space precisely. So it is called a translation. It is called a translation if there exists a vector V naught in V such that what I do is that I just map x to x plus V naught for all x in V. Okay, clear? So in this case we say G is a translation by this vector V naught. Okay, so what is typically happening here is that suppose I choose this point x, and let's say I translate this to by V naught, right? So I just add V naught to it, and suppose I land somewhere here. Let's say suppose I land somewhere here, then y will be corresponding landing suppose here. I translate it by V naught, and then I'll get the same vector which is just a bit displaced in the axis, like this. Suppose this is G of V, but still you can see that the distance between x and y is unchanged, right? So this should be suppose x plus v naught, this is x y plus v naught, but still the distance between them is unchanged. Clear? Okay. So now we come to the observation which actually I want to discuss in this very lecture, which is the relationship between orthogonal operators and rigid motions. So the theorem is as follows. Let f from v to v be a rigid motion. So evidently v is a real inner product space. I am not mentioning that anymore. So let f from v to v be a rigid motion. Moreover, I want it to be finite dimension, let's say, where v is a finite dimensional real inner product space. Okay. Then there exists a unique orthogonal operator. Then there exists a unique orthogonal operator, say T on V, and a unique translation G on V, such that this f is just doing the orthogonality first, or orthogonalization first, and then applying a translation to it. So it's just G composed with T. Okay. So provided any vector you choose out of this inner product space, if you orthogonalize it with respect to this orthogonal operator, and then you translate it to some point by some point, then you will still be in some sort of a rigid motion. And you can also conversely talk about it as well, because we have already seen that orthogonal operators and translational operators are individually, or rather I can say that, since see, this is pretty specific to understand, because orthogonal operators are actually linear operators which preserve length, right? So orthogonal operators are trivially rigid motions, because if you carefully observe that suppose T is orthogonal on V, then what is the norm of Tx minus y? So it's just norm of x minus y, which, because it preserves distance, sorry, it preserves length, but then Tx minus y is nothing but Tx minus Ty. So it's indeed a rigid motion. And if I talk about translation operators, then the vector by which the vector by which the translation occurs, that will eventually get cancelled once you take the distance between 2 points, right? So translations and orthogonal operators are trivially rigid motions. So if you take composition, so you are applying 2 rigid motions on a vector, you will still end up to a rigid motion. That's quite intuitive, right? And that easily follows from the definition as well. That is, if you start with any vector, and you first apply some rigid motion to it, so the individual distance between the points on that vector are still intact, and then you apply another rigid motion, but still it's intact, right? So applying 2 rigid motions on the same vector will still make you land in a rigid motion. What we are talking about here is a converse of it, right? That is, if you start with a rigid motion, then you will acquire a unique orthogonal operator on the same finite dimensional real inner product space, and you will get a translation as well, such that the rigid motion is nothing but a composition of these 2 operators. That is, first you do the orthogonal operator and then you do the translation. Clear? And the thing I said just before having this theorem can be verified directly out from here as well. That is, an orthogonal operator is just a special case to this, right? Because it is then by just a translation by 0. You carefully observe that an orthogonal operator is then just a translation by 0, Moreover, a translation can also be related to an orthogonal operator, because a translation is just then a special case of a rigid motion where we are doing an orthogonal operator with which is an identity operator. So translation is just orthogonalization, I will use this term only, which is equivalent to applying an orthogonal operator, orthogonalization by identity, right? Okay. So let's quickly see a proof of this. Proof. And the proof is rather simple. It just is a sort of a constructive proof. So suppose what I do is that, suppose I choose an operator T on V, and we define it as, say, T of x is f of x minus f of 0. Clear? First thing to observe here is that therefore T is a composition of f and the translation by f of 0 minus f of 0, sorry, the translation by minus f of 0. We also define, let f to be defined as G composed with T, okay, where G is a translation, by f of 0. I guess now it's clear. Now these two things are clear. Okay. Okay. Because if I apply a translation by f of 0 on T, I'll eventually land in f as well. So because the reason is quite valid, right? We are starting with a vector, say fx, we translate it by minus f0. So somewhere, suppose this is fx, so we translate it by minus f0. So suppose this is fx, we translate it by minus f0, suppose here, and then we again translate it by plus f0. So I eventually land in fx only, right? Clear? So therefore T is indeed a rigid motion, right? Therefore T is a rigid motion. T is a rigid motion. It will eventually follow from here only. T is a rigid motion. Now suppose I want to find the norm of Tx for any arbitrary vector x in V. Okay. So for all x in V, what is the norm of Tx? So the norm of Tx, by definition, it is norm of fx minus f0. Let me find out its square. So norm of fx minus f0 squared. But we are starting with a rigid motion, right? F is a rigid motion. That's exactly what is given as to f is a rigid motion. So this should be norm of x squared, or x minus 0 squared, so eventually an x squared. So this actually means that T is length preserving. And what are length preserving operators called? Orthogonal operators. But orthogonal operators, if it's linear, that's quite important. Orthogonal operators if T is linear. We have not yet established the fact that T is linear. We are only having the fact that T is length preserving. So if we can somehow prove that T is linear as well, then we can eventually claim that T is just an orthogonal operator, right? So now we want to prove that T is linear. Okay. So for that we first need some observations. Firstly, what is T of x minus T of y squared? Norm of T of x minus T of y squared. So if I directly apply the polarization identity, I will get norm of Tx squared minus 2 times norm inner product of Tx Ty plus norm of Ty squared, right? But norm of Tx squared is nothing but norm of x squared. We have already seen this. So this is minus 2 times inner product of Tx Ty, and here I have norm of y squared. If I apply the same to norm of x minus y squared, I will eventually land up in norm of x squared minus 2 times inner product of xy plus norm of y squared. And these follow from the polarization identity, as I just said. But what we have is that, but we have already seen that T is a rigid motion, right? But since T is rigid, so these two must equal, right? Therefore, so for them to be equal, what we only need is that the inner product of Tx Ty must be equal to the inner product of xy, right? Clear? Okay. Now Now, to establish linearity, we cannot go direct by any sort of a definition, because there is we are not saying about linearity of f at any cost, right. So, to establish linearity, if I somehow show that if I start with t of cx plus y, where c is some scalar, and so what I am trying to do is that, let me just write it down, because verbally it will be a bit confusing. So, we are starting with two vectors x, y and v, and we are starting with a scalar, okay. So, I consider the element x plus cy minus t of x minus c times t of y. I consider this element and I consider its norm. If somehow I show that this norm is 0, and since we have chosen arbitrary vectors xy and an arbitrary scalar c, so eventually I will get the fact that the norm will be 0 for all vectors x plus cy, but that will eventually mean that this complete operator is identically 0, or t of x plus cy must be equals to t of x plus c times t of y, which will eventually give us the fact that we have a linearity here. So, let us start with its square. And how do we evaluate this is that we consider it to be in this form, sorry, we consider this to be in this form. So, norm of tx plus cy minus tx, I consider this, minus c times ty, c square, okay. And what we do is that we again apply the polarization identity directly. So, this will be equal to norm of t of x plus cy minus t of x whole squared, and then I will get plus here I will get norm of c times ty whole squared, or which I can actually write as c squared times norm of ty whole squared, correct, okay. And then I have here minus 2 times the inner product of this with this, but I can then eventually bring c outside. So, minus 2 times c inner product of t of x plus cy minus t of x and t of y, right. Yeah. But then t is a rigid motion. So, I can write this as x plus cy. So, it is the norm of x plus cy minus x whole squared, and this is plus c squared times norm of y squared, because t is also length preserving, this we have already seen. And what do we have here is that minus 2c times, I can write this inner product as inner product of t of x plus cy, I can compose it with ty, correct, ty minus inner product of tx ty, correct. I can do this, right, okay. But then outside the brackets we have here c squared norm of y squared, and I have another c squared norm of y squared. So, I have 2 c squared norm of y squared, and we know that inner product of tx ty for all xy is just inner product of xy. We have established this here, right. Therefore, I can apply this to the element inside the bracket to get, so this is minus 2c times inner product of, so here I get x plus cy with y minus inner product of xy, right. So, what do I get here? So, I get 2c squared norm of y squared minus 2c times, so what I get here is inner product of xy plus c times inner product of y with itself minus inner product of xy. But from here you can see that this part cancels, and then you are left with here minus 2c squared inner product of y squared. So, this part also gets cancelled eventually. So, you are left with 0, but then this means that t of x plus cy is nothing but tx plus c times ty, okay. This implies t is linear, okay. Therefore, we have already seen that t is length preserving, therefore, t is evidently an orthogonal operator, therefore, t is an orthogonal operator. and G is a translation that we have already established in the definition. There is nothing too complicated there. Clear? So evidently the theorem is proved. The only thing which we are left is that to show uniqueness. Right. So how do we show uniqueness? So suppose we have vectors, say v1, v2 in V, and T and U are orthogonal operators on V, such that fx is a translation of T by V1 and is also a translation of U by V2. Okay, clear? And this happens for all x in V. But then if I apply x is equals to 0, for x is equals to 0, we will eventually get V1 to be equals to V2. Therefore, the translation comes out to be unique. Right? This implies the translation is unique. But once the translation is unique, this will eventually give you that Tx is equals to Ux for all x in V, which will imply that T is identically equal to U, and therefore the theorem is proved. Thus, any rigid motion corresponds to composition of translation and a orthogonal operator. Okay. So this is all for this lecture. In the next lecture, we will be starting the concepts of orthogonal projections. So meet you guys in the next lecture.